And we need to get through this section in one day, but there's only 4 problems, so it's definitely doable. Definitely doable. So properties of logarithms. We know a little bit about logarithms already, but here's the thing. If you want to talk about addition and you want to use subtraction to undo it, those 2 operations have to follow all the same rules. That's the only way it works. So if we want to know about properties of logarithms, all we have to do is go back to chapter 6 and talk about our properties of exponents. Because again, an inverse and its original function have to follow the same set of rules. So I think, what does that mean? Let's see if you can remember. How are we supposed to get the answer for that? I don't see a plus anywhere up there. How did you know you're supposed to add the exponents? It is a property. We had a property that said if you want to multiply 2 exponentials together, you are supposed to add the exponents. So if we want to multiply logarithms, we're going to have to add. That was a property. If it holds for exponents, it has to hold for the inverse, which is going to be logarithms. Then if we had this, x to the 8th over x to the 4th, what did you have to do? We had to subtract. So division was really subtraction. So if we see that they want us to divide, we're going to have to change that to subtract it. And there was another big one. And that one was this. If we had x to the 3rd and we wanted to square it, what do we do? Yeah. But again, it's not multiplication that we see up there. This is raising something to a power. So to raise something to a power, we're going to have to multiply. And depending what we're doing, we're going to use these forwards and backwards. If we see addition, we know that came from multiplication. If we see subtraction, we know that came from division. If we see a logarithm that's being multiplied by something, we know that came from a power. So these rules are the same rules we learned in chapter 6. It's just that we have to stop and think, okay, logarithms follow the same properties that exponents do. So I've got to use all of those rules. And this getting ready is a good one to show us how it works. It won't be real understandable at this point, but just follow along with what I have up on the TV screen here. It says, write a positive number on a piece of paper, then key this number into your calculator. So I think, okay, I'm just going to pick some number that has absolutely nothing nice about it. 23. Can't divide 23 by anything but 1 in itself. It's a prime number. It's 23. That's it. That's all you can do with it. So then it says, perform the steps shown here and press enter after each line. And at the end, see what happens. All right. So I'm supposed to take the logarithm of that answer. LOG, that answer. That's not a nice number. Then I'm supposed to take 2 times whatever I got there. 2 times that answer. Still not a very nice number. And then it says I'm going to take the answer and I'm going to add 4 to it. Okay, there it is. Now I'm going to take 10 and raise it to that power. Well, that's not going to be very nice. It is. And take the square root of that answer and divide it by 100. Recognize that number. It's the number I put in at the beginning. So what we're seeing here is that all of these steps somehow were inverses. You know, they took a step and then later on they had an inverse that would undo that step in order to make these things happen. Now, explain why this result makes sense. We won't be able to do that until after we do today's lesson. But what we're going to do and what we're going to learn today is the basics, which are that when we see multiplying, Logarithms, that means add, because they're in that same group with powers. And when we see divide, we subtract, because that's what our rules for exponents says we have to do. And then powers, raising something to a power, we know is to multiply. Now that's the one that usually, the rest of it people get right away. But where do you multiply a logarithm? I mean, where on earth would you put a number that you say, I'm going to multiply that logarithm by something? Think about it and think about what you already know about algebra. Let's just say I wanted to multiply this logarithm here by 7. Where would the 7 go? Is that multiplying the entire logarithm by 7? Does that multiply the entire logarithm by 7? It does. This doesn't say, hey, I'm going to take 7 and multiply both sides by it. We're not trying to get an equivalent expression. We're saying we want a vertical stretch of 7 on this logarithm. So when we multiply logarithms, it's going to look like that. The number's going to need to go out in front to get that multiplied. So our essential understanding is going to be logarithms and exponents have corresponding properties. We're not learning anything new. We're just using it differently with logarithms. That's all we're doing. Down here, this little box says exactly what I was talking through, everything in the exponential power properties that we had. For any positive numbers, m and n, and b, where b is not 1, we talked about that before, raising 1 to any power just gives you 1 back, so it's pointless. If you need to multiply, you add. That's what you do. So that's called the product property for logarithms. It was called the product property for exponents. Back when we dealt with chapter 6. Our middle one here says logarithm base b of m over n. Well, that's division. Division is subtraction. Fancy word for division in math is quotient. So that's our quotient property. You're supposed to divide. Okay? You subtract. And then the last one says, hey, if we have, and that's kind of tiny, something we're supposed to raise to a power. Oh, we already talked about that. That means multiply. What you do is you bring that power out in front and multiply by it. So this becomes n logarithm base b of m. And that is called the power property. Again, they're not new properties. We saw all these before in chapter 6. It's just remembering logarithms, and when we have bases with unknown powers, those are inverses of each other. They have to follow the same set of rules. They have to. So those were the rules that we learned before. The rules we're going to use now. All right. Simplifying logarithms. So using about what we know, what we just talked about, we want to figure out what would these really say. It says, what is each expression written as a single logarithm? Now, most books don't say it that way. Most books will call this condensing. When you condense something, you make it smaller. So what we want to do instead of log base 4 of 32 minus log base 4 of 2 is we want to be able to say logarithm base 4 of one thing and stop when we condense. Just one thing. Subtraction. Where did subtraction come from in logarithm language? Division. So this was really supposed to be 32 divided by 2. Well, I know what that is. That's 16. And if logarithm base 4 of 16 is something nice, we're supposed to find it. Snail shell it in your head. Is this something nice? 4 to some power is 16. What is it? It's a 2. It's a 2. So this is that step where we say, I'm not sure. Let me take a second and check. 4 to the x equals 16. Oh, yep, that's 2. Come on, this is really cool. Look at this. this is 2. It's cool. Let's go down here. Take a look at B. First thing you come across, awkward 6 out in front. Where did that 6 come from? It's multiplying, so where did multiplying come from? Power. But not the whole thing, or there'd be parentheses. It's just this times 6. So that means this little 6 was really x to the 6. And yeah, like Eli said, the 5 is really weird out in front too. But isn't that just another power? But just for this term, because it was just with this logarithm base 2 of y. Now notice this takes another step, and that's because we want to get those powers back up where they were first before we say, hey, addition. Where did addition come from? Multiplication. So we can still condense this further by showing, hey, that was multiplication. That's what it was. And then they took it and they strung it out and made it longer. That's called expanding. But we're going to do these forwards and backwards. Now this one's done because there's no way for us to know what x and y are going to be in advance. So if there's a number there, we should think through it and see, hey, is this something nice? But if it's variables, there really isn't a whole lot. Say, hey, you're done. So go ahead and give 1, A, and B in the got it a try, and then I'll check on you and see how you're doing. I'm seeing a lot of boo-boos on 8. If I asked you what 3x times 5x is, and there were no logarithms in that problem, what is 3x times 5x? 15. X squared. Yeah, some of you are forgetting a little squared there. Don't forget what you already knew. It is.
I got it, right?
Because as a variable, B is a very cool one. So keep going until you realize how cool it is. What does 2 logarithm base 4 of 6 minus logarithm base 4 of 9 really say? What does it say? 1. It says 1. So let's go through it, because there were a couple of people that were not getting that. So this 2 out in front, multiplication came from powers. So this was really 6 squared. We know what 6 squared is. It's 36. All right, subtraction. What's subtraction in logarithm language? Division. So this is really logarithm base 4 of 36 divided by 9. Hey, wait a minute, that's 4. Logarithm base 4 of 4, if we want to know if that's nice or not. We're going to put a little equals x over here. We're going to snail shell that and say 4 to the something is 4. Oh, yes, that's 1. That says 1. That's excellent. Our own little hidden language math that we have. All right, so down here at the bottom, one last thing. That's taking something bigger, making it smaller. We can also go backwards. We can take something small and break it apart into something bigger, because sometimes in calculus you need to be able to do both of those operations. So we're going to break these apart. What is each logarithm expanded? So taking it as one logarithm statement and making it into multiple logarithm statements. Gosh, that's tiny. That's a little better. Big picture of this problem is there's a fraction bar, and fractions are division. So the first thing I would ask myself is, what's division in logarithm language? That is subtraction. So I need logarithm of 4x minus logarithm of y. Notice how I had to add another logarithm in there. You always stick with the same logarithm all the way through. But I'm not done yet, because I'm supposed to take anything that needs to be moved, which would be any powers, any multiplication, and any division, and split it all up. So there's still some multiplication here. What's multiplication in logarithm language? Addition. Backwards, if it said condense, we'd look at that and say, okay, addition, that was multiplication, so that should be 4x. And then subtraction, we're going to subtract y, that means division, so it should be 4x over y. It has to work forwards and backwards. That's our expansion. Let's look at B. Very cool. Very cool. Logarithm base 9 of x to the 4th over 729. Big picture, still division. Still fraction mark. So what do we do for division? Subtraction. Now, there's an awkward little power up there. What are powers supposed to be? Okay, so does everything get the 4? This and this? Just this one. How do we know? That was the one term that had the 4th power. The 729 doesn't have the 4th power to it, so the 4 is just in front of this term. Now, there's a possibility that there might be one more thing that we can do with this problem, and that would be if the back end there snail shells to something nice. Is 9 to the something 729?
It looks like it might.
9 to the 3rd? So this says 3. Now we couldn't do that for the whole thing because there was a variable involved with the other piece. But definitely that was the 3rd power then. Alrighty. Let's see. Yeah, I think you can do both of these. Give them a try. There's no properties there that we just already use. Anybody without a calculator? It looks like.
Let's see if that first one was
Now, A is not done. At this level, at what we're doing today, yes, I would accept that, and you could say, hey, I'm finished. But there is a hidden cubic inside 250.
What?
Think about a number small enough that if we raised it to the third power, would divide into 250 nicely.
That's the problem. Six was like, I mean, 5 was like 250 or 243. So then I was
So
like,
you didn't have a lot of choices. Exactly.
is it like 0.5?
It's not, but you're getting closer. Perfect cube that divides into 250.
See, it's 240.
It's 5 to the third, everybody. 125. And let me just do it this way so I don't lose anybody. Two times 125 gives you 250, right? Now, how do you undo the multiplication? This is multiplying.
Yeah, I did not know you could do that. We have to do that with like the test or the quiz.
No, they'll be very basic. Oh, so which one of those shows up as something nice? Okay, so let's see how that works. So now it looks like this. Now we have power. Where do powers go? In the front. Not of the whole thing, but in the front of that term. So notice nothing works out beautiful and nice, but the nice part is that there are more powers hidden inside the powers. I know you're not going to appreciate that right now, but when you get to calculus, you'll appreciate being able to break things apart a little bit further. So, yeah, you're always constantly looking for what is my base, how can that help me to break apart more numbers? And that would be the full expansion. Like I said, right now, if we were doing a mini little quiz, I would expect most people to just stop right there. And with a little more experience on logarithms, yeah, we should be able to take it down here. But right now, today, doing this in one day, that's a lot to ask.
Yeah.
So let's go ahead and talk about change of base formula. We have seen logarithms with many bases, not just the two that are on our calculator. There are only two on our calculator, log, which we know is logarithm base 10, and ln, it's actually supposed to be a lowercase l and a lowercase n, but on your calculator it's a capital L and a capital N, because it looked like the word in, so they changed it to capitals. That is logarithm base e. So what about all the other ones? I mean, what if we need logarithm base 5? We need logarithm base 7. What do? Well, it turns out there's a very easy way to get your calculator to get those for you. And that's called the change of base formula. Change of base formula. And this is a formula that's just been used forever, as long as calculators have been around, to figure out numbers that aren't necessarily logarithm base 10 or logarithm base e. So any different base. And it's a very basic formula. And here's what it says. If you have any positive numbers m, b, and c, so we're not talking about negative bases or anything like that. The base is not 1. We've talked about that. 1 to any power is just 1. And c is not equal to 1. Wait a minute. Where does c business come from? Well, the c comes from the fact that this can't be done on the calculator exactly as it is, unless you have one of the newer models. What you have to do is say, okay, I'm going to do this in two parts. I'm going to take the logarithm of the number that I'm trying to evaluate, and I'm going to divide that by the logarithm of the base. Now, here's why it's called the change of base formula. It doesn't matter what the base is, as long as the base is exactly the same on the top and the bottom. So we can use logarithm base 10 for this, or we could use ln. Most people don't like using ln because it's got the obnoxious e piece going on, but either one of them will get us the right answer, which at first just doesn't seem to make any sense at all. Let's just say we're looking for logarithm base 3 of 11. What the change of base formula says to do is to punch this in as the logarithm of 11 divided by the logarithm of 3. And it says that will give us our answer. Let's check and see. If we need logarithm base 3 of 11, this formula says take the logarithm of 11 and divide it by the logarithm of 3. Now, how am I supposed to know that's true? 2.18 blah, 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 blah. Well, let's snail shell this. We're saying 3 to this power has to equal 11. So if I punch 3 in to that power, so there's my answer, it better come out to be 11, or this change of base formula stuff is wrong. There it is. It's 11. So change of base formula allows us to do exactly what the formula is called, change the base. You take the logarithm of the number you're trying to evaluate divided by the logarithm of base. So down here it says what's the value of each expression, and we realize this is just calculator work here. I don't have to do any of this in my head if I don't want to. Log of 27 over log of 81. Let's see. Log of 27, make sure you finish off the parentheses. If you don't, you won't get the right answers. Log of 27 parentheses divided by log of 81. And some of you right now are saying, but Cedarholm, I didn't have to do any of that because when I hit log, there's a little space there so I can change my own base. Well, when you take ACTs, you don't necessarily get to do that. They might give you what the log of 27 is and the log of 81, and you have to know to do that division yourself. Because this didn't come with decimals, we don't want decimals. Hopefully you recognize that as 3/4. If not, you hit math number 1, enter. Right there. Now, we could have done this our old way. Our old way was to snail shell this and say 81 to the x equals 27. And then say to ourselves, well, 81 is 3 to the 4th. So this would be 3 to the 4x equals 3 to the 3rd. 4x has to equal 3 for this to be true. So x equals 3/4. But we don't have to do that algebra anymore. Now it's saying, you know what? You can just grab a calculator and use the change of base formula. Did you already get B? And if they're not nice, we usually go 4 decimal places. That's, again, it's just history. These have been around for a long time, and it has just been standard practice to always go 4 decimal places. So 2.2266. Give us that. So go ahead and take care of the got it, 3A and 3B. Again, 4 decimal places. If it's not nice, if it is nice, write it as a fraction. A fraction for me, forgot it, 3A? 5/3. nasty decimal for B, right? What'd you get?
0.85.
Here we go. So change the base formula. We use when we don't have one of the fancy calculators that lets us physically change the base.
Can't you do math alpha A?
Some people can. Not everybody. The newer ones will do that. All right, one word problem here. Chemistry. Woohoo!
Done.
The pH of a substance equals negative log H plus.
That's
Gone? All right, so I guess we won't do the chemistry problem. Golly. It's nice to do things. You must have figured out that we wouldn't have enough time for that. Yeah. And I've got a little time to start on that. Very quick. Very good.
What is it doing?
Oh, it might, it's probably just condensed and expand. And some of them will be change of base.
Think about it, that's like,
Oh, 5 seconds.
this is gonna take like 4 hours.
Oh,
Take
it
like
is
4 minutes. It's so hard. It's gonna watch me like just finish it. That was a grind. It's gonna take like 4 hours. That's natural. I said 4 minutes. I think 4 hours.
Oh, yeah. Some basic condensing, expanding. There's a couple of them in there that might take you more than 20 seconds. Couple. But then change a base formula, that's just punch it in.
I'll take you longer. 20 seconds. Take me about.
Ooh, quick reminder, because you're gonna run into this. Square root is the same as what power? Square root,
2.
what power? 1/2. So don't forget things like that. Square root, 1/2 power. It's been a long time since we did chapter 6. Chapter 6 was the first chapter we started this semester with. And then we had to bounce around for the MCAs and the ACTs. Been a while.
Oh, a square root is like 1 over x squared. Oh yeah, I remember that. Yeah. I'm on number 10. Are they fun? Yeah, they're fun. They're fun ones.
Well, not all of them are fun, but some of them have fun.